Hello again. This is video lecture 10.3, and we're going to be talking about two sections in the book of chapter 10, section 4 and 5. Chapter 10, section 4 introduces the concept of kinetic energy of rotation. Now, we're well familiar already with the idea of kinetic energy of a particle, and that is the form of energy that the particle has merely because it's moving. And if the particle has mass m and velocity v at any given time, then its kinetic energy at that time is 1/2 m times the magnitude of v squared. Okay, now let's think about what we've been talking about in this chapter. Rigid body rotating about a fixed axis, like a disc or a wheel, rotating about a fixed axis of rotation. It's made up of little pieces of things, a bunch of particles put together. And they're moving. And if they're moving about a fixed axis of rotation, each one of those little particles is moving in its own circle. But they're moving. And each little piece of this thing has some mass and some linear velocity. So doesn't each little piece have some kinetic energy? It does. So how much kinetic energy total does a rotating rigid body have? That's what we're talking about in this section. Okay? All right. And I'm going to talk about it mostly by way of analogy with the linear case. So let's go to that first. Let's take an object with an actual finite size. How about a block, a rigid block? And just let it move along a floor or a tabletop or something, a horizontal surface. And just move to the right. And that's what's happening in this first drawing. I've got a block, it's on some kind of surface. I don't even care if there's friction, I'm not worried about that. And it's moving to the right, and it's a rigid object. So I can think of every little piece of that block, all kind of locked together in this rigid shape, moving to the right. And the point that I've marked in the middle, right there, roughly, is the center of mass of the block. It would be at its geometric center if its mass is uniformly distributed. And so the velocity of that point in the block is the velocity of the center of mass, VCOM. But it's a bunch of rigid things glued together to make the block, so every little piece of that block has the same V, VCOM. And every little piece is moving. So it's not hard to write down a formula for the total kinetic energy of the block. Now this block just sliding along a line, that's what you call linear motion, right? That's what we have been doing up through chapter 9. Here's a new word for that, by the way. Linear motion, where the object is just moving through space, is called translation. Because in physics, to translate through space means to move. So if you have what's called pure translation of a rigid body of mass m, you can write down a formula for its kinetic energy, although now we're going to call it the translational kinetic energy, K-trans. Translational kinetic energy. Just to all the pieces of the block moving in a line. It's 1/2 times the total mass, notice that's a capital M, times the magnitude of the velocity of the center of mass squared. 1/2 m total VCOM squared. And that gets you what's called the translational kinetic energy. It's important to be clear when you're talking about translation, because in the next chapter, chapter 11, we're going to see what kind of motion you get when you combine translation and rotation. So my first picture here is called pure translation. Just think of a block sliding along a line. Now let's go to our standard picture of pure rotation. Pure rotation of a rigid body about a fixed axis. This is a top-down view of something that looks like it's shaped like a disc or cylinder. And its axis of rotation is right through its center. At least that's the way we're going to draw it here. And as we watch it from above, the whole thing is rotating counterclockwise at some angular rate. And so I can talk about its angular velocity at any given time. And in fact, all points on the body have the same angular velocity. That was the previous video lecture. All points in a rotating rigid body have the same angular velocity. Okay, so how do we get a formula for the kinetic energy of all the little pieces of this disk as they go around and around in a circle. Let me draw one of the pieces. It'll be an arbitrary one. We'll draw it with a red dot right there. That's one of the little pieces of the disk. And at the instant I'm drawing the picture, that little piece has a velocity. I'm going to label it VI because it's piece I. And it has a certain radial distance from the axis of rotation, RI. So what's the kinetic energy of that one little piece? That's not too hard to write down because that's just a little particle. Particles can only translate, so their kinetic energy, the kinetic energy of piece I, is 1/2 m sub I magnitude of v sub I squared, because it's just that one little particle. But now what I'm going to do is I'm going to take advantage of the formula that we talked about in the previous video lecture that says that I can write the magnitude of the linear velocity of a point on a rotating body as the radius of its circular motion, the radial distance it is from the axis of rotation, that would be r sub I, times the magnitude of the angular velocity of the body, omega. Don't write omega sub I. You see why you don't need to do that? Omega does not depend on which little piece of the disk you're looking at. Every piece of the disk has the same omega. Now substitute this expression for the VI and square it in there. Let's see what we get for the kinetic energy of that ith little piece. We get 1/2 m sub I r sub I squared times absolute value of omega squared. And that's the kinetic energy of that one little piece. So, but I have a whole bunch of little pieces that make up the disk, and they're all moving around in a circle, so they all have kinetic energy. So what's the total? Okay, to get the total kinetic energy, I'll come over here, K total, I will sum over all the little pieces, I, the kinetic energy of each piece. 1/2 m sub I, r sub I squared, absolute value of omega squared. Now, you're probably still not too comfortable with this summation notation, but the things that don't depend on the sum symbol can kind of be grouped by themselves, whereas the things that do depend on that index I need to be grouped together. So I'm going to write the expression like that. I've kind of grouped the 1/2 and the omega squared, and then in the middle I've got the sum over I, m sub I, r sub I squared, the things that depend on which particular particle you're talking about. And then the next thing everybody does is just define that quantity in the parentheses. Sum over all the particles, take the mass of each particle times its radial distance from the axis squared. The symbol for that quantity is a capital I. Its name, let's write down here, it's the rotational inertia of the body about the specified axis of rotation. That's the name for that symbol. It's called rotational inertia. FYI, I'll just let you know, it's also sometimes called moment of inertia. But I prefer rotational inertia. I think that's a little more explanatory, as I'll say in a minute. So when all the dust is settled, what you've got is the total kinetic energy of a rotating rigid body about a fixed axis. We're going to call that from now on rotational kinetic energy. And the formula for it is right here. K rotational. 1/2, still that 1/2, times I, the rotational inertia of the object, times the magnitude of its angular velocity squared, its angular speed squared. That's our new kinetic energy formula for a rigid rotating body about a fixed axis. So let's say a little more about that rotational inertia. Look at the formula we use to define it. Go particle by particle through the disk. Take the mass of each particle, multiply that by its radial distance from the axis squared, and add them all up. Okay? So it depends on the mass of the object and how far the mass is, the mass of the pieces of the object and how far each piece is from the axis. So it depends overall on how much mass this thing has that's rotating and how it is shaped. I basically depends on two things: how much mass is there and how is it distributed from the axis relative to the axis of rotation. At the end of the day, you can think of rotational inertia as a measure of how difficult it is to change the object's angular velocity about the specified axis. After all, inertia, for linear motion, is a measure of how difficult it is to change a particle's linear velocity. Now we have the rotational analog of that. Rotational inertia is a measure of how difficult it is to change a rotating body's angular velocity. Let's practice a little more with that formula for calculating rotational inertia. Let's start with the simplest scenario, a system that consists of a bunch of point particles called point masses. Okay? Let's talk about calculating the rotational inertia for a system of point masses about a specified axis of rotation. So let's have something specific to visualize. My drawing here is a side view of what you might call an artist's mobile. All right? And when an artist makes a mobile, they tend to have some kind of structure where there's a central axis, vertical axis for support, and then various objects are hung off of that axis, and the whole thing can rotate about that central axis. That's often what a mobile is. So let's imagine that that's what this picture is. Here's the central vertical axis, right, going up and down there, and some objects are connected to it. In fact, 3 point masses. There's mass 1, M1, connected by a very light rigid rod that is a perpendicular distance R1 from that axis. Then we have particle M2 of mass M2, which is on a very light, i.e. massless, rigid support that connects it to the central axis, but not at a right angle. Therefore, I've also drawn in the picture a dashed line that you can see is the perpendicular distance from the mass M2 to the axis, and that's labeled R2. And then the third particle, M3, is connected by a light massless rod that is indeed perpendicular to the central axis, and its distance is R3. And this whole mobile can rotate, say like that, about that vertical axis. What's the rotational inertia I of this mobile? Where we assume that the only things that have real mass are those particles. Particle 1, particle 2, and particle 3. Well, to get rotational inertia for a system of point masses, use that formula right there that I just had on the previous slide. You can even, in fact, still see it right up above. You do a sum. Use an index, we'll call it I, going from 1 to n, where capital N is however many particles there are. You take the mass of each particle times Ri squared. Be careful, though. Ri is the perpendicular distance of mass I from the axis of rotation. Perpendicular distance of mass I from the axis of rotation. So in this case, to calculate the rotational inertia of that mobile, I would take the value of m1 times that distance r1 squared, plus the value m2 times the distance r2 squared, and then plus m3 times r3 squared. Note, if this were a Wiley plus problem, quite likely what they would do would tell you, like, for example, the length L of that angled rod, and then maybe tell you that angle right there, call it theta. Then you'd have to figure out R2 using trig from L and theta, because you got to note that it's that R2 distance that has to be used to find I. So, to emphasize what I've said already, rotational inertia depends on the masses of the objects and their perpendicular distances from the axis of rotation. That is to say, in general, I depends on the mass of a body and how that body's mass is distributed relative to the axis of rotation. And I can say even more. The more mass there is farther away from the axis, the larger the rotational inertia. Because when the mass is farther away from the axis, it's harder to change the angular velocity of something like that. Okay, so first thing you need to be able to do is that if we give you a system comprised of just point masses, little spheres, little point masses, use this formula right here correctly to calculate the rotational inertia of the object. All right, now I'm going to go on to Chapter 10, Section 5. So the reading there would be Chapter 10, Section 5, calculating the rotational inertia. So this gets at the following idea. What if the object that is rotating isn't just just a handful of a couple or a few point masses, but is a fully extended body rotating about a fixed axis, like that disk I just showed you up above. Let me draw that again. Top view. Okay, and fill it in. It's a solid disk with an axis of rotation there through its center. And it's rotating with some angular velocity about that axis. You can't just use the formula I circled in red to get I, because that's for a finite system of point masses. What we've got now for this disk is an extended body, which really is an infinite number of infinitesimal point masses. Technically, you have to convert that sum up there to an integral and do an integral. We're not going to ask you to do that, okay? We're just going to tell you for some common shapes and specifying some common choices for the axis of rotation for that shape, what's the formula, the correct formula to use for the rotational inertia I for that shape. Here you just go to Chapter 10, Section 5 in Wiley Plus, and there is a very, very important big figure / table that shows a bunch of shapes. You got to tell me the shape of the thing and where the axis of rotation is, and then tells you the rotational inertia. I'm going to show you that table on this slide. It's probably not going to show up very well, so remember that this is in the book, okay, in Section 5 of Chapter 10. This table shows rotational inertias for some common shapes. This has to be a go-to table for the rest of Chapter 10 and the next Chapter 11. Okay? You use this as a reference in any of the homework where it's useful. What are some of the common shapes that we might be studying that would be rotating? I'll just go through them briefly one by one, starting in the upper left. We have what's called a hoop. A thin hoop with a total mass m and a radius r. And the axis of rotation runs right through the center, perpendicular to the plane of it. Okay? Now, don't worry about how you would contrive the axis to be that way. Don't worry about that. Let's just take that as given. You've got a very thin hoop. It's got a total mass m. Let's make sure that's clear. It's got a total mass m, and it's got a total radius r. And it's rotating about that axis. What's the rotational inertia for that shape? It's right down there. Simple. It's the simplest one. Take the mass times the radius squared. Because every piece of that ring is the same distance from the axis, r. Or hoop, I should say. All right, that's the easiest one. The next one we'll use once in a while. It's a thick hoop. A hoop with some finite width to it. The book calls it an annular cylinder or ring. It's a thick hoop. Okay, it's still got some total mass. We'll call that m. And it's got an inner radius, r1, and an outer radius, r2. So r1 is from the central axis to the inner surface of the ring, and r2 is from the central axis to the outer surface of the ring. And then the axis goes right along the central axis there of the ring. And it's rotating then about that axis. What's the formula for the rotational inertia for something like that? It's right down there. I'll write it right here. I equals 1/2 m times r1 squared plus r2 squared. I'm not saying that's immediately intuitively obvious. Formally, it has to be derived by an integral. We're not asking you to worry about doing integral. So the price we pay for that is you just have to take that result in faith. That's the formula for the rotational inertia of a thick hoop, a ring. Next, let's basically take that ring, the second picture, and fill it all in with mass, uniformly distributed. So that's a solid cylinder, also called a disk. It's got some total mass m. It's got some radius this way, r. And it's got a length this way, l. And then the central axis runs right down along its center. And the whole thing is rotating about that axis. What's the rotational inertia of a solid cylinder, also called a disk, which is the picture I was just showing you right there in the top view. That's what this entry is about, that shape. But there I'm looking at it from above. What's the formula for the rotational inertia of a disk? This is probably the most commonly used one. The formula for I is, because it might be hard to see there, 1/2 total mass times radius squared. Notice the L doesn't even come into it. The length of the cylinder along the axis direction doesn't even matter. You can make it as long as you want that way, and it's not going to be any harder to spin. That's the most commonly used entry in this table, in my opinion. Next entry, row 2. Take that exact same kind of cylinder or disk, but instead of rotating it about an axis along its central line, take the axis through its center but perpendicular to its central line. So now the axis is drawn going up and down this way, and it's rotating that way. So if I think of this pen as being my disk, in the first case it's rotating about the long axis of the pen. In this new case, it's rotating about an axis this way. That could happen. It still has mass m, radius r, length l. Now what's the formula for the rotational inertia? Now it's different. Depends on where the axis is. And it's kind of hard to see, so I'll write it right above. In fact, it's so hard I have to take my glasses off to see it. It is, ready? 1/4 mr squared plus 1/12 ml squared. All right. Next, another common case. A thin rod about an axis through the center and perpendicular to the length. So here what you want to imagine is the solid cylinder in picture D that I was just talking about, but let that radius r that I had before, right there, shrink to effectively so tiny that we'll ignore it. That's called a thin rod. It's just a cylinder that's much longer than it is thick. And then it turns out the only thing that matters, notice where the axis is though, up and down like that, and it's rotating about that axis. Now that all that matters is the mass m and the length l. And the formula for the rotational inertia, right there, is 1/12 ml squared. Just take the earlier answer and drop the 1/4 mr squared because the r is so small. We'll use that one a lot too, case E. Okay, case F is a solid sphere. Solid sphere. Here all you need to know are its mass m and its radius, from distance from the center out to the surface, r. The axis of rotation is any diameter. They're drawing one that's vertical. Doesn't matter. Just got to go through the center. And it's spinning, rotating about that axis. What's the formula for the rotational inertia about that axis? It is, it's hard to see, so I'm going to write it, 2/5 mr squared. Again, that's not intuitively obvious. You have to do an integral to prove it. We're just going to state it. 2/5 mr squared. Solid sphere rotating about any diameter. Next picture. Watch out, because it's exactly the same picture as F. Now we're in G, though. And the words tell me, because the picture is the same as F, that it's a thin spherical shell rotating about any diameter. So what you can't see here is that the inside of this is hollow. It's still got some total mass m and some radius r, but all that mass is out in a very thin shell out at r, and that the rest of the inside of this is hollow. And then the axis of rotation goes through the diameter, goes along any diameter, I should say, and the thing is rotating about that axis. The formula for the rotational inertia of a thin spherical shell is given, and I'm just going to tell you what it is, because that's hard to read. 2/3 mr squared. Let's compare F and G. Let's say both things have the same mass m and the same radius r. But in F, the mass is distributed throughout the whole body inside the sphere, nice and uniform. And in G, the mass is all out at the outer edge, and the inside is hollow. Notice the rotational inertia values are slightly different. For the solid sphere, it's 2/5 mr squared. For the shell, it's 2/3 mr squared. Which one's bigger? Which one has a bigger I? It's the thin shell, right? 2/3 is bigger than 2/5. Why does a spinning spherical shell have more rotational inertia than a solid sphere of the same mass and radius? Because with the shell, all the mass has to be way out at the edge. And remember, the rotational inertia is sensitive to how much mass and how far is it from the axis of rotation. The farther from the axis, the bigger the contribution to I. That's why a thin shell has a larger rotational inertia than a solid sphere. H takes the very first shape, a hoop, but instead of rotating at about a central axis, it rotates as the axis goes through along any diameter of the hoop. And now the thing is rotating about that axis. Still mass m, radius r. And now the rotational inertia is 1/2 mr squared. Not the same as part A, even though it's the same shape. Thin hoop, mass m, radius r, but a different axis to rotate it about. In part A, rotational inertia was just mr squared. In part H, where the axis is along a diameter, it's half that. Why is it smaller in H compared to A? You see why? Or why is it larger in A compared to H? You can think of it that, you can ask the question that way. The reason is in A, all the mass m is distance r from the axis, all of it. But in H, some of the mass is closer to the axis than r. That's going to make the rotational inertia less. And it turns out to be exactly 1/2 mr squared. The last shape will come up every once in a while. It's kind of the shape of like a book. The book calls it our text calls it a slab. It's a rectangle. It's got some total mass m. It's got a width a and a length b. Okay? And the axis of rotation is perpendicular to it, going through its center, and that's what it's rotating about. What's the rotational inertia of that? It's written down here. I'll write it out. 1/12 total mass times width squared plus length squared. So we will use that if we have a shape like that. Now, one thing to note about all of these values in this table, these 9 values. all these axes of rotation pass through the center of mass of the object. Let's note that. All axes pass through the COM of the object. That's important to note. They might go through the center of mass and then go along a length or perpendicular to it, but they still go through the center of mass. So you can go to use these whenever you have, and I want to emphasize this, one of these shapes with one of these axes, exactly as you see it. It's got to be one of the shapes here with one of the axes here. And you can't play fast and loose with where the axis is. If the axis isn't in the place that you see in this table, one of these entries in this table, you can't use this table, at least not directly. I will emphasize. Rotational inertia depends on mass and shape and where the axis of rotation is. Now, let me take springboard off of that idea and point out that we very commonly have a situation that violates what I've just been talking about. That we have a rigid body rotating about an axis of rotation, but the axis of rotation is not through the center of mass. So even if it's a nice simple shape, I can't directly use that table I just showed you. What am I supposed to do? Okay? All right, let me show you with the shape here that I've got. A flat object. It's a piece of wood that actually is shaped like a pentagon, a polygon with 5 sides. It's not a regular pentagon, but that's okay, it's a pentagon. And its mass is relatively uniformly distributed. And by a simple little experiment, you can locate roughly where the center of mass of this pentagon is. We've drilled a couple of holes in various places. You could suspend it from a hole. You could then see how it hangs at rest vertically. You could draw a line underneath that hole. You could do that from 2 holes and look where they cross. They'll cross roughly right about here. That's roughly where the center of mass is. So now let me hold it horizontally. If I take my pen as my axis, and if I let this thing rotate about the pen through the center of mass, then that's an axis of rotation perpendicular to the plane of this thing and through the center of mass. If this shape were in that table, I could go to that entry in the table to use I, because that's an axis through the center of mass. What if I take this thing and put my axis not through the center of mass point, but through one of these other holes over here to the side, like over here? Now it's not going to the center of mass, and I still have it rotate about that axis. You could do it. How do you find the I for a case like that? So notice there's the axis through the center of mass and perpendicular to the pentagon. That'll be ICOM. And then there's the rotational inertia for the axis over here to the side. Notice when I hold the pen in the 2 axis locations, the pen is vertically up in both cases. The axes that I'm talking about are parallel to each other. But what I want to know is how to find the rotational inertia about this shifted axis over here. For that we need, which I'm going to state without proof, you want to see the proof, read chapter 10, section 5. We need what's called the parallel axis theorem. Theorems can be proved. You want to see the proof? Read section 5. But I'm just going to tell it to you because you have to be able to use it to solve problems. I've drawn a picture with a hexagon. And you're looking down from above. And one possible axis of rotation, and I've taken the hexagon to be regular in shape with a uniform mass distribution. So the center of mass would be through the geometric center, COM. If we put an axis of rotation through that point, then, and it's spinning about that, then you would need to use for I what we would call ICOM, the rotational inertia about an axis through the center of mass. And if my table I just showed you had an entry for a regular hexagon, I could go straight to that because the table would be for the axis through the center of mass. But suppose what I actually have is not a vertical axis through the center of mass, but a vertical axis through this point P, where that big black dot is. And that axis is displaced over to the side from the center. And we need to know how far it's displaced. By a distance, we're calling h. Okay, so the center of mass axis is perpendicular to the screen in the middle. And then there's a second axis through point P, right? We have a second axis through this point P, and parallel to the first axis through the center of mass. And the distance between those parallel axes we're going to call h. So back to the pentagon, there's the axis to the center of mass. So the I about that is ICOM. And then here's the displaced axis parallel to the first one. And if I call that over there point P, the I for here would be IP. And the distance between that axis and that axis would be this distance right along here from one axis to the other, and the picture calls that h. If you know ICOM, you can then get I for point P, and that's the parallel axis theorem. Here it is. The rotational inertia for the axis about point P, the axis displaced from the center of mass, is equal to the rotational inertia for the axis through the center of mass plus a positive quantity. So more. What do I add on to ICOM? I take the mass of the whole thing times the distance h, the perpendicular distance h, between the two parallel axes squared. That's the parallel axis theorem. Note then that the rotational inertia about that displaced axis P is always going to be larger than the rotational inertia through the center of mass axis. Always. Because the parallel axis theorem tells me that IP equals ICOM plus a positive quantity. That basically means that the easiest configuration to rotate a rigid body is when the axis is through the center of mass. At least compared to this one. If you take any axis parallel to the center of mass one and displace it, like over here, it's going to have a larger rotational inertia. It's going to be harder to change its rotation. Let me emphasize this result, the parallel axis theorem, is used a lot in the rest of Chapter 10 and Chapter 11. Why? Simple. We many times have a body that's rotating about an axis that's not through its center of mass, okay? The body is not rotating about an axis through its center of mass. We'll see. Just wait. So we will use that parallel axis theorem a lot. All right, I'm going to leave you on the video today with a class engagement exercise that you can do on Blackboard. Let me show that to you. Okay, so this will be a class engagement exercise that you are to just type in your answers on Blackboard. And it goes like this. We have a figure below that shows 3 disks from top view, each with a uniform distribution of mass. They have a radius each and a mass each, and that's given for each. If you want to call them A, B, and C, here are the radii values, here are the mass values. For disk A, the radius is 1 meter. The mass is 26 kilograms. So these are pretty big. For disk B, the radius is 2 meters. The mass is 7 kilograms. For disk C, the radius is 3 meters, and the mass is 3 kilograms. Okay? 3 disks with uniform mass distribution. Each disk can rotate around its central axis, perpendicular to the disk face and through the center. So you're looking at the axis of rotation edge on, that's coming out of the screen, and it's right in the center. It's those 3 black dots. And each of these things can rotate about that axis of rotation. A. For each disk, I want you to calculate the rotational inertia I for an axis through the center and perpendicular to the plane of the screen, the axis we just show there. For each disk, I want you to give the answer for I, right? I'm asking you to calculate I, and yes, this would be ICOM in unit of, that's the SI unit of rotational inertia, mass times radius squared, so kilogram meter squared. And then part B. Suppose I construct a compound object by That should say, by the way, I'm sorry, that should say stacking. S-T-A-C-K-I-N-G. By stacking disk A on top of B, center on center, and then stacking them together on top of C. So you get like a tier, with C at the bottom, then B, then A. Okay? All three have their central axes aligned. Question: what is the rotational inertia, ICOM, of this compound object in the SI unit of kilogram times meter squared? I just want you to enter your answer. And that's the class engagement for Monday. All right? So that's all for this video.